Welcome to Quantum, where we explore the deep connections between physics, mathematics, and the structure of the universe. Today, we dive into the world of supersymmetric quantum mechanics through the lens of MiniBFSS and its mass-deformed cousin, MiniBMN. These are not just mathematical curiosities, they're simplified laboratories for exploring M-theory, black holes, emergent spacetime, and holography. The MiniBFSS model is a simplified cousin of the BFSS matrix theory, originally proposed as a non-perturbative definition of M-theory. Unlike its parent, the mini version retains only a subset of degrees of freedom, fewer matrix coordinates, and fewer supercharges, but still captures essential dynamics of supersymmetric quantum mechanics. This simplification allows us to probe deep quantum effects, such as supersymmetry breaking, ground state degeneracies, and dual geometric interpretations, without the overwhelming complexity of the full BFSS model. MiniBMN models are built by introducing mass terms which preserve maximal supersymmetry. These deformations mimic the physics of D-branes in curved backgrounds, such as PP wave geometries. In 9 matrix models with 8 supercharges, we recover the well-known BFSS-BMN structure. As we reduce the number of matrices, the supersymmetry algebra changes. The 3-matrix version, for example, links to SU21, while the 1-matrix version is even simpler, yet still encodes fascinating quantum behavior. Now let's talk about the dual gravity side of the story. For the BMN matrix models in more than one dimension, that is, for D greater than 1, the dual description in M-theory is known as the bubbling geometries. These are intricate, curved backgrounds in 11-dimensional supergravity, capturing the dynamics of branes in a highly symmetric and controlled setting. They offer a geometric realization of the matrix quantum mechanics, embedding the matrix degrees of freedom into smooth, curved spacetime. In contrast, for the BFSS matrix model, which is the undeformed version of the theory, the dual gravity background is much more specific. It corresponds to the black zero-brane solution in type 2a string theory. This geometry describes a stack of D0 branes collapsing into a black hole, and it serves as the holographic dual of the strongly coupled quantum mechanics at finite temperature. But the most intriguing case is the BFSS model in one dimension, known as BFSS2. This model is special because its dual gravity description appears to be governed not by a black brane or bubbling geometry, but by an ADS2 spacetime. This hints at a deep connection between the matrix dynamics in low dimensions and the rich physics of near-horizon geometries of extremal black holes, where ADS2 plays a central role in holography, quantum gravity, and even models of quantum chaos. The BFSS models are best understood as gauged supersymmetric quantum mechanical systems. Their conceptual roots can be traced back to early work on supersymmetric quantum mechanics, where matrices evolve in time under both bosonic and fermionic dynamics, all while respecting a local gauge symmetry. Let's start with the basic ingredients. The dynamical variables of the theory are matrices, Hermitian matrices, representing spatial positions of D0 branes in a higher dimensional theory. These matrices live in the adjoint representation of the gauge group, which is usually taken to be UN. Each matrix corresponds to one spatial direction, and the number of matrices determines the dimension of the target space. Conjugate to these bosonic matrices are their momentum variables. Just like position and momentum in classical mechanics, these form the foundation of the model's phase space. The entire system is then made supersymmetric by introducing fermionic matrices, real spinors, that also transform under the adjoint representation. To make the fermionic sector compatible with the rest of the model, we use a real Clifford algebra, a mathematical framework built from anti-commuting gamma matrices. The dimensionality of this algebra depends on how many bosonic matrices we have. And interestingly, the allowed numbers of matrices and corresponding supercharges follow a beautiful mathematical pattern with periodicity mod 8, much like in Bott periodicity. Now, the full dynamics are encoded in the Hamiltonian and the supersymmetry generators. The Hamiltonian includes three main contributions: kinetic energy from the bosonic matrices, a Yang-Mills-like interaction involving their commutators, and a Majorana term coupling bosons and fermions. Together, these terms describe the quantum mechanics of a system of interacting branes. The supersymmetry generators, or supercharges, govern how the bosons and fermions transform into each other. Their algebra ensures that the system remains supersymmetric under time evolution. Importantly, the algebra closes only when the Gauss law constraints are satisfied. These are the mathematical conditions that ensure gauge invariance and project us onto the physical Hilbert space of the theory. Within this formalism, the generators of the gauge symmetry appear as conserved charges. They enforce that all physical states must be singlets under the gauge group, meaning they remain invariant under gauge transformations. A key result comes from applying Feer's identities, mathematical rearrangements specific to Clifford algebras. These lead to a constraint that ties the number of supercharges to the number of bosonic matrices. Specifically, the number of supercharges is always twice the number of matrices minus 2. This elegant relation selects 4 special cases for the BFSS models. When we have 2, 3, 5, or 9 matrices, we get 2, 4, 8, or 16 real supercharges, respectively. These are precisely the models that appear in higher dimensional string theory and M-theory contexts. For instance, the 9-matrix model with 16 supercharges is the original BFSS proposal for a non-perturbative definition of M-theory in the infinite momentum frame. In summary, the BFSS matrix models offer a deep and elegant formulation of supersymmetric quantum mechanics. By combining matrix dynamics, gauge symmetry, and supersymmetry, they capture the essential features of stringy degrees of freedom in a reduced, yet still rich, quantum mechanical framework.